All right, so we're going to take a look at square roots today. Square roots are a vital part of what it is that we want to cover later on in this chapter with special right triangles. So it's really, really important that we do a review with you of the concepts that were already covered in algebra dealing with square roots. So when we talk about a square root, there are two parts that end up making up every single square root. There's the radical, which is your square root bar, and then the stuff on the inside, which is called our radicand. And anytime you take the square root of a value, you are actually looking for what number times itself would end up giving us the radicand. So in our case, if we took the square root of 25, we know that 5 times itself would have given me 25. So the square root of 25 is 5, which you already knew. Or you could also kind of say that it would be a negative 5, because if you were to take 5 and square it, you get 25. You would also be able to get 25 if you took a negative 5 and squared it. So when you take a square root, you're basically looking for what number times itself would give you what's inside of that square root. Now that leads us to perfect squares. And perfect squares are when you take a square root and you get a whole number out, you're dealing with a perfect square. So if I say that, you know what, you've got to know all of these values. You've got to know that 0 squared is 0 and 1 squared is 1 or 5 squared is 25. Make sure you know them all the way up. You know that 9 squared is 81, 10 squared is 100. Make sure you know 11 squared and 12 squared. It's not bad to know 13, 14, 15, and 16 squared. That's pretty much where it goes. Anything higher than that is a bonus, but you really want to know through 16 squared. If I could take a square root, okay, say a square root of 0, and I get a whole number out, we know that 0 is a perfect square. Or 1. Since I take the square root of 1, I get a whole number out, 1 was a perfect square. Square root of 4. Pops a whole number out, so 4 is a perfect square. The next one in the list, 9 is a perfect square, because if I take the square root of that, I get 3. So anytime I take the square root of a number and get a whole number out, I know it was a perfect square. So for example, the square root of 121 is 11, because 121 is a perfect square, and 11 times itself gives me 121. So we're talking about perfect squares because when you simplify radicals, you always want to be able to look for perfect squares. So 1, 4, 9, 16, 25, 36, those are my perfect squares. All of these values listed over here, these are my perfect squares. When I deal with square roots, though, I can actually multiply. This is the first property that we're going to talk about, is the product property, meaning multiplication. If you're working with two square roots, say the square root of a and the square root of b, and you're multiplying them, you can really rewrite it as a multiplication of the two radicands inside of one big old square root. The opposite is also true. If I have a square root of a quantity a times b, and both of those are in the inside of my square root, I could rewrite it as the square root of the first quantity times the square root of the second quantity. So an example that we're going to take a look at is the square root of 5 times the square root of 7. By our product property, that would allow us to say, really, it would be the square root of 5 times 7. And we know that the 5 times 7 gives me a 35. So the square root of 5 times the square root of 7 is just the square root of 35. So that's the product property for square roots. The next property we're going to take a look at is the division property for radicals. Now, you can go ahead and divide within a square root. Okay, so if I've got square root of a divided by b, you can then split it up. You can split it up into the square root of a over the square root of b. Also, the reverse is true. If I had the square root of a and I'm dividing by the square root of b, I could then make it one big old square root and say it would be the square root of a divided by b. Now, sometimes that's a good property to know because then it helps us when we're trying to simplify. So, for example, if we take the square root of 25 divided by the square root of 16, I can split that up by my division property and make that the square root of 25 divided by the square root of 16. Now when I look at that, I know that the square root of 25 is 5 and the square root of 16 is 4. So sometimes it's just easier to be able to apply these properties so that I can simplify my radicals. There's a reason why this next boxed statement is written down with stars. It's huge, 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 huge. You gotta make sure that you know that the addition on the inside of a square root does not mean that you are allowed to just then take the square root of the first and then plus the square root of the second. Nor could you do a subtraction on the inside and split it up as a subtraction of the two quantities. You are not allowed to do that. You can only add or subtract square roots that are like square roots. So make sure that anytime you see a plus or a minus sign on the inside of a square root, please do not split them up and make it the square root of the first quantity minus the square root of the second quantity. That is not legal, as I say. But could I, however, if I have this same type of square roots, add them or subtract them? Absolutely. And here are a couple examples. So in the first example, I've got 2 square roots of 3 plus the square root of 3. Since these two quantities have the same type of square root, you are allowed to add them. It's almost like saying, oh, I've got 2 of this plus 1 of this, so then I should have a total of 3 of those. Kind of like 2x plus x. You get 3x. Same thing happens here. 2 square roots of 3 plus the square root of 3 gives me 3 square roots of 3. In the other example, we're taking a look at, it's got 10 square roots of 6 minus 3 square roots of 6. As long as the square roots are the same, you can put them together. So if I've got 10 of them over here minus 3 of them over here, when I do the subtraction, I will get 7 of them. So 7 square roots of 6. So you're allowed to add or subtract only like square roots. Now, anytime you need to simplify a radical expression, so simplifying a square root, it must follow the following 3 rules. The first off, the radicand, the thing that's on the inside, can have no factor other than 1 that is a perfect square. So if the thing that's sitting on the inside, the number that's sitting in the inside of my square root, if it can continue to be broken down with perfect squares, you have not simplified it fully. You have to make sure that you break it down as much as possible. The second rule says that the radicand, the thing on the inside, cannot be a fraction. So anytime you have a fraction with inside of your square root, you need to take care of that. You are not allowed to have fractions inside of your square roots. The last rule says that no radical is allowed to be in the denominator of a fraction. So if I say have 1 divided by the square root of 2, I cannot leave it. That is not in simplified form. That square root needs to be out of the denominator. And I'll show you how to work through that with an example later on. So a couple examples, and that's really what we're going to do now, is we're just going to run through some review examples for you from algebra. And the first one we're going to talk about is the square root of 80. So my job is, when I take a look at this problem, I say, okay, is this simplified as much as possible? When you look at 80, 80 isn't really exactly broken down as much as possible. There are actually a couple ways in which I could break this down and work with perfect squares. The easiest way to hopefully break this down is to realize that 80 is the same thing as 16 times 5. So if I did 16 times 5, notice the square root of 16 is 4. So when I take the square root of 16, it kind of jumps to the outside. Don't forget it's there, it's kind of small. It jumps to the outside, and then when I look at taking the square root of 5, I can't take the square root of 5, so it has to stay on the inside of my square root. So my answer that is simplified is 4 square roots of 5. So that's the easiest way to do that one. If, for some reason, you figured out, oh, okay, maybe I didn't think of 16 times 5. Maybe you thought of something like, I don't know, some students will do 4 times 20. Now, is there anything wrong with that? No, there's not, but you're going to work at this a lot longer than the person who came up with the 16 times 5. Well, if you did this, the square root of 4 is 2, and then so you'd have 2 square roots of 20. Now, the question is that reduced as much as possible? No, it's not, because we know that 20 can be reduced down even further. 20 is the same thing as 4 times 5. So if I did 4 times 5, the square root of 4 is 2. That would pop outside. What you do then is you take those two values and you multiply them. So I would get 4, and then square root of 5 would be remaining on the inside. Notice, I get the same answer. However, notice how much more work I had to do. So your job is to try to pick the largest perfect square that radicand would break into or factor down into. So in the next one, if we take a look at this one, I've got 27 on the inside. I'm going to rewrite that. And 27, perfect square that is in 27, is 9. So it would be 9 times 3. I'm going to leave the x squared for a second. So here's what happens. The square root of 9 is 3, so that pops out. I can't take the square root of 3, so that stays on the inside. That's not a perfect square. X squared, however, the square root of x squared is an x. So I've got all of that on top, and I've got that front number of 8. So what we do is we multiply all of those values. And we multiply them, we get 8 times 3 is 24, times x, so we get 24x. And remember, you had a square root of 3 on the inside. So right now, 24x squared to 3 is my answer. So for C, notice we've got an issue in this case because we have a square root in the denominator. We are not allowed to have that. So the best way to get rid of a square root in the denominator is to multiply the top and the bottom by that problem. So we're going to multiply top and bottom by the square root of 3. Multiplying, we're going to go multiply straight across. So I get 12 square roots of 3 over, now this is where it kind of gets a little tricky if you don't remember. When you take and you multiply two quantities like this, you're going to take the whole numbers that are sitting out in front of the square roots and you're multiplying. So this is a 5 and there's a 1 in front of that square root of 3. So 5 times the 1 gives me a 5. So we're going to write that down. And then square root of 3 times the square root of 3. Well, when you multiply square roots, you're going to multiply the inside. So square root of 3 times square root of 3 is square root of 9. However, we know that that's a perfect square. So the square root of 3 times the square root of 3 is 3. Now, before I go any further, though, I do realize that I can take the 3 from the bottom and the 12 from the top and reduce it down. And when I reduce it down, I'll get 4 square roots of 3 over 5. So running through, making sure in the radicand here is that as simplified as possible. No factors other than 1 are perfect squares. Good deal, that matches. Number 2, I don't have any fractions in my radicand. Good deal. Third thing, I do not have any radicals in my denominator. So it fits all the rules. This is simplified. I know it may look weird, but that is my answer. Next one for D. So in D, notice I've got a quantity squared. I tell my students, anytime I see a quantity squared, I always write it out twice. Write it out twice, write it out twice. So when I write this out twice, I get two fractions, and all I have to do is multiply them. When I multiply fractions, I go straight across. So we're going to multiply. I get 5 times 5 on the top, which gives me 25. And on the bottom, when you multiply, square root of 5 times square root of 25 is the square root, square root of 5 times the square root of 5 is the square root of 25, which is just a 5. So, simplifying, we end up getting 5. Hopefully you noticed in this example, square root of 5 times square root of 5 gave me a 5. And the other one, square root of 3 times the square root of 3 gave me a 3. Anytime you take the square root of a quantity times itself, the radicand is what you get in the end. So, next one. Notice in E, I've got square root of 16 divided by 2. Could I split this up? Could I make it the square root of 16 over the square root of 2? Absolutely. However, what I'm going to do is I'm going to notice. Do you realize that 16 divided by 2 is really just an 8? So I'm working with the square root of 8. And the square root of 8 can break down into 4 times 2. Now we know that the square root of 4 is a 2, so pop that down on the outside. And the square root of 2 that I've got left on side, I can't do anything with. So my answer is 2 square roots of 2. F. Before I can do anything with F, notice, remember, if I'm trying to add two square roots, they have to be like square roots. So I need them to be the same type of square root. So I've got the square root of 12. Now that's not simplified down. I know that the square root of 12 is the same thing as 4 times 3 because I'm always trying to break those square roots into perfect squares, one of which is a perfect square, and 4 is a perfect square. So then I'll put the plus square root of 3 so I don't forget it. Square root of 4 is 2, so that pops on the outside. So I get 2 square roots of 3 plus the square root of 3. And my final answer, since I had 2 square roots of 3 plus 1 square root of 3, I get a total of 3 square roots of 3. So now that you've had enough example problems, I believe, why don't you go ahead and try the next 3 here, G, H, and I, on your own. And when you're ready, go ahead and start the video up again, and I will have my answers written down for you. Alright, so let's go ahead and take a look at G first. So I had 5 square roots of 2 quantity squared. And remember, when I said before was anytime you've got a quantity squared, write it out twice. It's the easiest way to deal with it. So if I write it out twice, I get the 5 squared roots of 2 times 5 squared roots of 2. Anytime you're doing a multiplication like this, you want to multiply your whole numbers first and then your square roots. So 5 times 5 gives me the 25. Square root of 2 times square root of 2 gives me square root of 4, which is just a 2. Remember we talked about that. If I have the square root of a quantity times itself, it's just whatever was sitting on the inside of that radical, the radicand. So 25 times 2 ends up giving me 50. In the next one, same process. I've got a multiplication of two quantities here. Take the whole numbers and multiply them. 6 times 2 gives me 12. Square root of 3 times square root of 2. Now those are different square roots, so we're just going to multiply their insides, and I'll get square root of 6. I can leave square root of 6 because it does not have a factor other than 1 that is a perfect square. So this abides by all of my rules, and that is as simplified as it gets. In the last example, square root of 60 breaks down into 4 times 15. 15, you might be thinking, well, yeah, 15 breaks down into 3 times 5. But the problem is 3 is not a perfect square, and 5 isn't a perfect square. Therefore, there are no ways in which I can break square root of 15 down. So if I take the square root, though, over here, the square root of 4 was a 2, so that pops out to the outside, and the square root of 15 is still there. So I had 2 square roots of 15 minus the square root of 15. That ends up subtracting, since I had 2 of them here and 1 of them here, I end up getting 1 square root of 15. Do I have to put a 1 in front? Please don't. It's kind of like putting a 1 in front of an x. We just, at this level, we just know it's there. So we end up getting square root of 15 for our answer. Now, since this was a review for square roots, you're going to get a worksheet. Make sure that you guys are asking questions. You learned it in algebra, but some of this stuff might be a little on the tricky side. Please, please, please make sure that if you're running across any problems, you let us know. All right, any questions? Let us know tomorrow. Otherwise, have a great night.